Hey guys, it's math video number 3. Last class we talked about making bigger diagrams. Today we're talking about making smaller diagrams, so scale diagrams and reductions. A reduction is a diagram that's smaller than the original object. The question is, why might you create a diagram that's smaller than the original object? Well, the main reason to do that, as is said here, is to make the diagram a more manageable size. Right? Many items are too large to draw on paper, so a smaller version of the object must be made, and that's our reduced diagram. So for example, these diagrams of dinosaurs here, clearly they are smaller than the actual dinosaurs would be, and you can see how large they actually are in comparison to a man. Diagrams that are reductions have a scale factor just like enlargements. Right? In enlargements, it was how many times bigger the diagram is. In reductions, it's telling us how many times smaller the diagram is. So enlargements had scale factors that were larger than 1. Reductions today have scale factors that are smaller than 1. All right, they will be less than 1, but they will be greater than 0. Right? Because if it was less than 0, then they'd kind of be like turning it inside out, and that's not possible. So all of our scale diagrams today will be 0 point something when they're decimals, or if you write them as a fraction, the top number will be smaller than the bottom number. So for example, a scale factor of 1 over 2, again, top number smaller than bottom number, means that the diagram is half the size of the original object, just like the buttons below. So here's a couple of buttons. The original button is 6 centimeters long across, and then the reduced diagram here is half the size, it's only 3 centimeters across. And we find scale factors of reductions the same way we did last time with enlargements. You take a length on the diagram, and then divide it by the corresponding length on the original object. So again, write this fraction down, length on the enlarged diagram over length on the original object. So we have, again, diagram on top, actual object on the bottom. The only thing is the length on the diagram will be smaller than on the original object because we're making a smaller diagram. So again, the top number will be smaller than the bottom. Please note that it might be easier to understand what's going on when we write the scale factor as a fraction rather than a decimal. So for example, if we have 1 centimeter on the diagram of a house, and then if that equals 150 centimeters on the real house, then the scale factor would be 1 over 150. Right? On the diagram is 1, on the real house is 150. So this tells us what we need to know. However, if we are given a scale factor, so if we're given this scale factor, for example, and then we're asked to find a length on the diagram, so say you're told that a house is 100 or 1,000 centimeters long, and we want to figure out how long would that be on the diagram. We could use this, but we can also turn this into a decimal and multiply. So for here, it'd be 1 divided by 150, and we'd get 0.0067. So decimals are still useful, but this doesn't really tell us as much information just looking at it as this does here. Scale factors may also be written as a ratio rather than a fraction. So we can write this one as a ratio. Remember, ratios have the colon in the middle. So we read this here as 1 to 150. So it's telling us again 1 centimeter on the diagram is 150 centimeters in real life. So let's take a look at some examples. So the first example here, spiders again. I know they're not fun to look at, but I think they look pretty cool, even though I don't like them myself. What we want to do is determine the scale factor that was used to create this scale diagram. All right, so again, we always take the length on the diagram, which is 15, put that on top. Remember, we go diagram over actual. So the diagram length is 15 centimeters, and the actual length is 24 centimeters. All right, so now we can do a couple of things with this. We can reduce this fraction and leave it as a fraction. So let's do that. Right, I can see right away is both of them can be divided by 3. Right, then we get 5 over 8. Okay, so that means the diagram is 5/8 the size of the actual spider. And we can also turn this into a decimal. So we can go 5 divided by 8. And what do we get there? Well, it'll be 0 point something because the top number is smaller. Let's find out. We go 5 divided by 8. We get 0.625. Okay, so that's these here are both scale factors of my diagram. Okay, another example here. We want to draw a scale diagram of this octagon. 8 sides means it's an octagon. And then we want to use a scale factor of 1 over 4 to create my new diagram. Again, this means that the diagram will be 1/4 the size. So each of these lengths will be 1/4 of the length. So what I want to do is I want to turn my fraction here into a decimal. That'll make life a little bit easier for us. I know that 1/4 is the same thing as 25 cents, so it's 0.25. So that means I want to multiply each length on this diagram here by 0.25. But notice I only have 3 different lengths. I have 6 here, here, and here. I have 2 here, here, and here. And then I have 4 right here and right here. So I only need to do 3 multiplications. So I can go 6 times 0.25. I can go 4 times 0.25. And I can go 2 times 0.25. So basically the way we can figure this out is by saying, okay, well, I know that each time I count here, that means I'm taking 1/4. So it's like adding up to $1, right? So here, if I have 6 quarters, that means I have $1.50, which is 1.5 centimeters. Okay, so on the diagram, 1.5 goes here, here, and here. With 4 quarters, that's equal to $1. That's just 1 centimeter. All right, and 4 goes here and here. And then if I had 2 quarters, that's the same thing as 50 cents, so 0.5. And again, that goes here, here, and here. So I used my scale factor of 1/4, and I used my lengths on my original diagram, and I figured out what the lengths would be on my reduced scale diagram there. So that's one way to calculate what lengths will be on the scale diagram. Okay, and one more example here. Here's another way to solve this type of question. The question says, the diagram of the killer whale was reduced by a scale factor of 1/57. So for every 1 centimeter on this diagram, I have 57 centimeters in real life. So remember, when I'm setting up my fractions, I have diagram over actual, right? So with my scale factor, I have 1/57. So that's diagram and actual. And then I can use the length off my diagram. So 16 centimeters here is on the diagram, and that corresponds to the length of the actual whale. I'll call that W for whale because I don't know that length. So to solve for that, we want to cross multiply. All right, so that means I'll end up with 1 times my W equals 16 times 57. 1 times anything here is just 1, or just that thing. So I'll have W equals 16 times 57. Let's figure that out. That's tough to do in your head. So 16 times 57 equals 912. So equals 912 centimeters. So that means the length of the actual whale is 912 centimeters, so just over 9 meters. So this is another way, another type of question that could be asked. Yeah, so hopefully you enjoyed this video. Don't forget to answer the questions on the Google form, and I will see you tomorrow.